Here's what we're going to cover. We're going to cover some things on drilling. And drilling is, what do you do when you drill a well? Analysis of the drilling data. Do you do well logging? Do you do DSTs? What all do you do when you drill a well? And you cement production casing in. And, it sounds simplified, but that's the 30-minute overview version. This is a typical drilling location. This is a drone shot of a well that we drilled earlier this spring. You can kind of see some of the components here. Here's the casing being prepped to run. Of course, the drilling rig is here. You've got pits for drilling mud, which we'll talk about later. We've got station number 2 back here. And then here's the actual dry mud, the doghouse, where all the activity takes place. And this is the most important little piece of the puzzle right here as far as geology. And those guys are concerned because those guys are responsible for telling us whether or not we've got a well or not. So what they do in here is very important. So on completion and production, we've got several topics to cover there, which this is the engineering portion of it. And we've got completion, perforating, stimulating, equipment sizing. What kind of equipment are you going to use? Your primary production. Are you going to have a field to develop? Is there anything here? Is it a one-hit wonder, or what is this thing? And then secondary and tertiary production. Seth kind of touched on the enhanced oil recovery, and he mentioned secondary water flooding. The enhanced beyond secondary is tertiary, which may involve polymer floods, may involve surfactants, just all kinds of different things to actually separate those remaining droplets of oil, which we call residual oil, that's typically unmovable, unproducible, and get those to be produced so we can enhance our oil. This is a tank battery. Many of you may have seen these. There's several different components here. These are the stock tanks. Usually paint the water tanks back here. You always have to have a water tank because it seems like every well in Illinois produces water at some point. And then this is the separator. It separates the water and the oil, and it goes through the various tanks. So what do we do when we drill a well? We've got to have a geologist tell us this is the spot. He says right here, this is what we're going to do. We're going to drill this well right here, and this is why. And us engineers, we argue back and forth with the geologist. We say, no, we think maybe it needs to be 10 feet this way, or no, we don't do that. But we say maybe it needs to be over here or whatever. But the geologist tells us this is the spot we need to drill a well, so we go out, and the state of Illinois and every other state in the union requires a drilling permit. So you've got to stake the location, they GPS it, they get the lat long, they get all of that, and that's where the well is going to be drilled. So then we move in the rotary rig, and the rotary rig drills with drilling mud. They drill the well, and during this process, this drilling mud's very important, and we'll go over this again, We'll go over this again, but it conditions the wellbore, lubricates the bit, carries the cuttings to the surface. We've got some cuttings you'll see at Stephanie's location. I think I've even got a bag of cuttings back there. And then it provides weighted fluid for control of the well. Has anyone ever seen any of the old movies of whenever they were, Tulsa, Boomtown? Any of those movies where the gushers, we don't like that. That makes a big mess. John Rockefeller back in the 20s may have sent oil down the creek trying to get it to a place where he could offload it, but we don't do that anymore. It's a hazard. We just don't do those things. So that's what the drilling mud does. It provides well control. So while you're drilling, it's very important to monitor the drilling time, how many minutes per foot or feet per minute, depending. Sometimes it's feet per minute. Most of the time, it's minutes per foot. And typically, you may see a drilling break that's 2 or 3 minutes per foot. If you're in a real hard chert or a real hard shale or something like that, it may be 10, 12 minutes a foot. Take the samples. The geologist, he goes into his little trailer there and he inspects the samples for shows. He actually puts it under a black light, and of course everybody should probably remember, you know, the Beverly Hillbillies and black gold, and you put it under the black light, and yes, there is black gold that shows up there. So he also looks for indications of porosity. What kind of rock is it? You know, are we in sandstone, are we in limestone, carbonates? You know, what kind of rock are we drilling through? It's all very important because that determines what we do with that well, even if there's a show. So here's a typical oil reservoir. This is kind of an anticline. You can see here there's some impervious rock at the top. We've got a little gas cap here. We've got our oil here and water, and you know, some mountainous things going on here. So we drill our first well and we say, man, this is great, and it looks like it's going to produce all oil, and it does. So we get excited, we come in, we drill another well. And it makes a little bit of water, but still a pretty good well. So we're still excited, so we drill another well, and we just miss it. And that's the oil business. Seth mentioned that. You know, 25% on a wildcat project is a real good percentage because many of those don't hit. You know, if you're in an established field, you may drill 10, 12 wells in a row and set pipe on all of them. They all be good wells. But there's a lot of dry holes in between good wells. So once we've got our well drilled, we do our tests. You know, we may just do a drill stem test. We always well log, and these are the geophysical logs. Hopefully, and this is part that will come later. Jeff Hoy and some of the others will show you actual well logs from a well, where you'll be able to see all the squiggly lines. Porosity, just remember this. This is what I tell the guys out in the field if they're wanting to know how I know this is a good well. Porosity, good porosity will always go to the left. Resistivity, you want that to go to the right. So that's a way to tell. If you can get those to match up, your geologist tells you you've got a show in that, hey, you're well on your way to saying, hey, we may have an oil well here. So we've decided that we do have a well. So we pull out the drill pipe, the 30-foot long pieces of drill pipe that we put in the well to drill the bit. We run the production casing in, typically 5.5, 4.5 casing, sometimes 7-inch, depending on what we're going to do with the well. And then we circulate cement slurry down the casing and up in between the outside of the casing and the borehole of the well to hydraulically seal that well bore. So it's actually sealed off from everything going up and down the well. Jerry Robinson, a little bit later in the day, he'll get into a little bit more detail here. So you displace the cement with water or mud to leave the inside of the casing usable, clear. You don't want to have to drill out cement. That's extra cost, so you don't want to do that. And then you release the rig and you prepare for completion. So what does it take for a well to produce? You know, Gary and Dale and all those guys, Jeff Hoy, they come in and they say, okay, this is the well. As an engineer, I'm interested in two things. And those two things is how much oil is there and how fast is it going to produce. So how do I know, as an engineer, how much oil is in that well? Well, we start out with this basic calculation right here. We have a pore volume. Remember we said there's porosity in the well. It may be 7%, it may be 15%, it may go as high as 22, 25%. But I need to know the saturations. That's what S stands for. SW is saturation of water. SO is saturation of oil. SG, saturation of gas. It's all going to add up to 100%. I'm interested in this right here. And I've got a calculation called Archie's equation that helps me calculate that. We actually calculate SW, and that gives us at least the amount of water that's in the well. That's what Archie's equation does. So I figure out my SO, I deduced, worked back, I put in some kind of factor for gas, and I calculate back, get SO, I have reservoir pressure. You know, typical reservoir pressure in a well is going to be somewhere close to freshwater gradient. Freshwater gradient of fresh water anyway, is 0.433 psi per foot. So if I'm at 3,000 feet with my well, I'm going to have a reservoir bottom hole pressure that's going to emulate somewhere around 1,300 pounds. So I've got that. For my logs, I've got the porosity and void space. I may not know the permeability yet, and permeability is Darcy's equation. And Darcy's equation, we'll actually get in it. I didn't realize here until I started talking about Archie's equation. I don't have Archie's equation in here, but Jeff Hoy does, and he usually gives you that before I get to this. So I'll have to put that in for next year, so in case this happens again. But permeability is how the fluid flows through the rock. And Darcy, he was more interested in filtration systems in Europe, but he developed this equation. It applied to the oil field, and we were able to use it, and so we do. Reservoir extents, how big is this reservoir? So we do all this, we get everything all ready, and we say, okay, we're going to complete this well, we're going to do our gamma ray neutrons so we can correlate our logs, we're going to perforate our intervals, we're going to decide on what stimulation treatment we're going to do. Are we going to frack? Maybe we don't have to. Maybe we just stimulate the well with hydrochloric acid, or maybe we do acetic acid or something like that. What are we going to do? We've got to keep the well under control. We always want to have the well under control, and then we schedule the completion rig. Want to know if our cement that we pumped in is good, so we run a cement bond log. May have an example of that a little bit later on in the day. Got your gamma ray neutron, you correlate, you perforate, and then you stimulate. Then you put the well in production. Okay, how much oil is it going to produce? We test the well, by swabbing. It's actually just kind of a temporary pump. It goes in, it's got cups on the bottom, and it pulls up through the casing, and you actually recover the fluid that comes through the perforations. So that fluid comes into the well bore, we pull it out, we get a test, calculate our percentage of oil, percentage of water, get a show of gas. Do we have gas to surface? Do we have 1,200 foot of gas in the hole? All of these things are recorded. So, part of sizing the equipment is the production rate. So this is the Darcy flow equation. This is the engineering portion of the talk this morning, and I think I'm doing all right. So we've got Q equals minus 141.2, which is a constant. You have K, which is permeability. You have H, which is height of the reservoir. You have pressure initial, pressure final. This little mu symbol is viscosity, and L is the length of the pressure drop, or in this case, we're going to use the wellbore radius, because you can drill a well on 10-acre spacing, and there needs to be 660 feet between the wells. So that's what we're going to use. So we've got this little sample problem here, and we're trying to determine the flow rate. Our permeability is 3 millidarcies, 7 foot of height, got a 50 psi pressure drop. 3.7 centipoise is our oil, and our length of our pressure drop is 660 feet. I know you probably don't have your calculators out, so here's the answer to that. You plug those in, and then Q equals 60.71 barrels per day. So that's our expected production rate at those parameters. So the other part of the equation is, we determined how fast. Now what do we do with how much? Okay, is this a one well wonder? And there's plenty of those out there. I drive by a couple of locations and there's a well and you're saying, man, that well's been there forever and there's no other wells around it. Well, there might have been at one time, but they were plugged. There's a well over in Wayne County, Illinois that was drilled in 1955 and it's produced, I don't know, probably by now 170,000 barrels of total oil. And it's the only well in that zone that still remains. All the other wells were plugged, that were drilled in the 50s, were plugged in the 60s because they just didn't last. And here this one well has produced 170,000 barrels of oil, which is a lot for one well. You know, a typical well, if you can get it to produce 50,000 barrels, that's great. This well's produced 3 times that much, still going. The average production over this, I don't know, 74 years or whatever, the average production's 4 barrels a day. Tremendous well, but it's the only one out there. So, original oil in place, what do we do with that? How much is there out there? Okay, you've got your barrels per acre foot, which is 7,758. You can calculate that, you know, using footage and acres and et cetera. You got your oil saturation decimal, your reservoir acres, your porosity decimal, and then your thickness. You'll notice a couple of things here always come in. The height. The height is always important. How thick is that reservoir? You know, it just bears to reason that a 3-foot reservoir versus a 20-foot reservoir, I would rather have a 20-foot reservoir at 10% porosity than a 3-foot reservoir at 20%, just because it's a whole lot more volume. All right, so if you go through that calculation, you can determine what your reservoir extent is. And what are you going to have to do? You've drilled one well. This geologist has brought you this project, and you've got a real good well. At least 60 barrels a day is pretty good. You say, well, what are we going to do now? Are we going to drill more? Well, then you go back to your geologist, and he says, well, the trend seems to be going this way. And typically, a trend in the Illinois Basin, this is not 100% true, but it's generally true. Southwest to northeast is the trend. So typically they're going to start, if you drill a well here, you're going to say, okay, I'm going to start looking here. I may not drill there, but I'm going to start looking here because this is the generalized trend. You know, we've got to use every bit of information that we have. And there's maps out there you can get on a website called IL Oil. And if you want to just pull up the wells, you can see the trend. The trend is there, and it's southwest to northeast. There's other places within that where it may go the other way, or it may just spread out this way. Sometimes it follows an old river channel. So that's what makes it exciting for the geologist is he just, you know, he's got to keep on his toes. The maps constantly change. We drilled 4 wells this spring. Totally wiped out the maps for the geologists. They had to change them all. 4 wells in amongst 17 that were already drilled. So you take all your data, you put it all, you know, you're going to drill some dry holes because you're going to find a spot out here where the reservoir ends. You know, it doesn't go on forever. So you're going to drill dry holes, but you are going to determine the extent of the reservoir. You're going to interpretate the data, you're going to get your structure, you're going to get your net reservoir, you're going to get your height, your porosity. All of those things are going to be created from isopachs. And again, I know I'm kind of touching on this, and this is introductory for you, but some of this stuff you'll see later on this morning. So we've got our well on production. We've got to monitor our total fluid production, our oil and water rate. We keep track of all these things. We got to create a decline curve. The well declines. We plot that. We determine how long the well's going to produce. What's going to be our time of abandonment? All of these things. Pressure buildup. How is our reservoir pressure doing? Is it well below our point 433 psi per foot. Then we've got other things. We've got surface and subsurface equipment that we got to maintain. We get scale and corrosion because we've got water production, all the minerals that are in there that cause carbonate scale, that cause iron, all of the scale and corrosion control. Keep track of the declines. We get to the point where we say, hey, this reservoir, we're about ready to put it on enhanced recovery of some kind. Typically, secondary recovery is going to be first. Is it a candidate for secondary water flood? Is it going to be a candidate for tertiary floods? So that's kind of a nutshell kind of overview very quickly on drilling and producing Illinois oil. I know, again, you can't cover a topic that's taken, since the 1860s to develop all the way up to 2019 in 30 minutes, but that's a general overview.